Okay, yes, pass up your homework. All right, so 6.1, the inverse sine, cosine, and tangent function. Let's start with sine, okay? Sine. So we know that the sine wave looks something like this. Okay, y equals sine x. The problem with y equals sine x is it's not 1 to 1, right? It is not 1 to 1. So if it's not 1 to 1, how can we talk about inverse functions at all? You know what I mean? We said yesterday only a function that is 1 to 1 has an inverse. So only 1 to 1 functions have an inverse function. Right? So far this doesn't make much sense to even talk about this topic. But it turns out we kind of need to. We need to talk about the inverses anyway. So what we're going to do is we're going to get in here and we're just going to choose this portion of the sine wave, namely between negative pi over 2 and positive pi over 2. We're going to just take this little piece with endpoints, completely inclusive here. And this is going to be called y equals sine x with a capital S. Literally with a capital S. That S there means you're only doing this piece. Okay, I mentioned that yesterday. So this is called the principal sine function. The principal sine function. Okay, and for the principal sine function, it has domain from negative pi over 2 to positive pi over 2, and range negative 1 to positive 1. Now, why are we choosing this little piece? Well, that little piece is 1 to 1. It passes the horizontal line test. There are other pieces that we could have chosen that pass the horizontal line test, but this is the one most mathematicians agree on. Okay? So we're going to pick that piece, and now we can define an inverse function. The name of the function is y equals inverse sine of x, but it has also been known as y equals arc sine of x, and I've seen people capitalize the S on the sine. I've seen people capitalize the A on the arc sine, but in this book, this is the notation they use, this first one right here. Okay? But please understand that it is the inverse of the red curve above, not the black curve up above. The black curve has no inverse function. Okay. So what would it look like? Well, its domain and range will be the opposite of the domain and range for principal sine. So the domain is going to be x's between negative 1 and 2. I'm sorry, negative 1 and 1. And then the range will be the negative pi over 2 is less than or equal to y is less than or equal to y over 2. So domain and range flip-flop there. So we're going to be drawing between negative 1 and positive 1 on the x-axis, and on the y-axis between negative pi over 2 and pi over 2. I also want to remind you that pi is roughly 3.14. So when I say pi over 2, what I'm really referring to is about 1.57. That's why I didn't draw it, super high up on the y-axis. It's really not much further out than 1. It's between 1 and 2. You can actually find graph paper on the internet where the y-axis is labeled in terms of pi. Okay? Just so you know. All right, now it's time to sketch the function. Well, we know that this function in red up above fits nicely in this box here. See? And when we draw our inverse function, it should fit nicely in this box here. So the box here is a Mr. Short thing. I just draw boxes. I don't know anyone else who does that. But you'll notice that the red curve extends from corner to corner on this box, right? Notice also that the red curve is entirely occupying quadrant 1 and 3, right? There's nothing in quadrant 2 and 4. Only point that's an exception is the origin. That's not really in the quadrant. But when this thing is reflected, it should still occupy quadrants 1 and 3. Okay? Which is why I'm glad you asked the question earlier about which quadrant the points will end up in. So we can sort of sketch this out. We know that this point, which is at pi over 2 comma 1, will end up at the point 1 comma pi over 2. So it truly is in the upper right corner of this box. And this lower left corner on the principal sine function is at negative pi over 2, negative 1. But upon reflecting it, it's just going to end up at negative 1, negative pi over 2, which is down here. So I'm a little zoomed in. We know that the principal sine function contains the origin, 0, 0. When that point gets reflected, it should still be at 0, 0. And now it's time to connect the dots. So, how do you connect the dots? Well, if you gave this to a child, they would just draw a straight line. Right? We can't do that. We have to understand one more thing. The curvature is going to be the opposite of the principal sine function. In other words, you notice like this right here, it's kind of a smiley part of the graph. See how it's kind of happy right here? It's like a smile. It's more like a smile than a frown. You see that? That's really important. See the curvature right there? This is called the curvature. It's more like a smile than a frown, I would say. Okay, that's going to be reversed when we draw this. So this part's going to be sad. Okay? And over here, you can see how right after the origin between 0 and pi over 2, the graph looks more like a frown than a smile. We call that concave down. That means it's on the inverse graph, it's going to be smiling on that side. So the concavities will switch. That's a really important idea for calculus later. But I'm trying to get you to sketch this properly. This part is more frowny, and the right side is more smiley, to put it informally. Okay? A little too steep in here. Actually, I need to mellow this out a bit. The slope should never exceed 1. Okay, that's a fairly decent graph. That's good enough. When you make your note card tonight, you're not going to have to stress out about that because you're going to include not only these 3 points, but at least 4 others on this graph. I'm talking about points in here, like right here. Like, what's that point? Well, that would correspond to this point here. Remember, if this was pi over 4 root 2 over 2, then we should have a root 2 over 2 comma pi over 4 on this graph. See? So I just gave you one possible point you can pick tonight. But I'd like 4 more in addition to what I have here. Okay? I would also like you to describe not just where 5 or 6 points are, but the parity. That means whether you think this is odd, even, or neither. Okay, let's go on and talk about cosine now. Okay. Okay, so let's just sketch the same kind of thing. So we know that cosine is an even function. So it looks like this. You'd think after 15 years I could draw these really, really well, but I still can't. Okay, so this is y equals cosine x. Okay? It's not 1 to 1. Can you highlight a portion that would be 1 to 1? Why don't you try that real quick on your paper. See if you can highlight a portion of this that is 1 to 1. Okay, so most mathematicians agree that we should highlight this part of the cosine wave, namely from 0 to pi. Of course, the range is still negative 1 to 1. Complete with endpoints. I'm not sure why they chose to make them closed endpoints. Listen, this is just mathematicians making decisions. Okay, I think the reason they have them closed is because they want to be able to answer questions like, what is the inverse sine of 1? Whereas if you leave an endpoint open, you might not be able to answer that question. So this is the graph that we choose. Its name is y equals cos x, right, with a capital C. It's pronounced principal cosine. Okay, we can write down the domain. Y equals cos x has a domain, what? 0 less than or equal to x, less than or equal to what? Pi, right? And the range, of course, is just negative 1 to 1. There we have it. Okay, so we come down to draw this on the, when we go to draw the actual inverse, we need to switch domain and range around, right? Okay, so we can say that the name of the function is going to be y equals inverse cosine of x, also known as arc cosine of x. It's another name for it. Domain and range switch roles. Domain is now negative 1 is less than or equal to x is less than or equal to 1. Range is negative from 0 to pi, excuse me. Inclusive. So here on the x-axis, we still are limited between negative 1 and 1. On the y-axis, we don't need any of the negative y-axis, but we do have to go all the way up to pi, which is 3-ish, 3.1. Let's do our green box again. This is sort of optional. That green box is going to end up here. The box is really for tomorrow's discussion. Okay, we just got to make sure that we graph this properly. It's a little bit trickier now because we do have a couple of points down there in quadrant 4, see? Well, a bunch of points. This graph definitely has some quadrant 4-ness, which means it's going to end up reflecting into quadrant 2. So we've got to be really careful here. Why don't we just label a couple points, reflect those points, and then try to connect the dots properly. So this is the very famous point 0, 1. Where is it going to end up? 1, 0. Okay, so we know this point's on the graph. This is the very famous point pi over 2, 0. Where's he going to end up? 0 pi over 2. Where is that? So right there. So this is 1, 0. This is 0 pi over 2. And lastly, this bottom right point on the principal cosine function is pi negative 1. Where's that going to end up? Negative 1 comma pi, which is upper left corner of the box. So it's always a good idea to reflect a couple points so you get the basic gist of it. Now we're going to connect the dots. We can do that sad happy thing that we did before. So just looking back at the graph here, I would say this part of the graph is kind of sad. So I drew a little frowny face there between 0 and pi over 2. See that? And the second part of the graph is more like a smile. So turn that frown upside down. That's a happy part of the graph. I don't know if you can see my little happy face. I'll redraw it. It's fun to draw happy faces. This part of the graph is happier than it is sad. So we're going to switch those around. The first part, that's on the left, is going to be sad, and then it will go happy and then sad, I mean. So this is going to go like this. This will be easier for you than for me because you're going to have 4 or 5 intermediate points to connect. So it's going to be a snap. I'll give you one of them like I did last time. This purple point on the top graph, right here, is at 3 pi over 4 comma negative root 2 over 2. That means you will have the point negative root 2 over 2 comma 3 pi over 4 on this graph. This will be the point negative root 2 over 2 comma 3 pi over 4. That's one of many points that you should add to this picture tonight. That's supposed to be a 3 pi over 4. Okay, so maybe put in a few more, which means you might want to draw this bigger. And don't forget to describe what you think it is in terms of parity. Do you think it's odd, even, or neither? Okay, let's go on and do the last function. That's the tangent graph, and that will be the conclusion of our lesson. Okay, so tangent has asymptotes at pi over 2, and 3 pi over 2, there's actually an x-intercept at pi and at 0. Okay, on the left we have an asymptote at negative pi over 2, and let's draw one more at negative 3 pi over 2. Some of you knew where to put the asymptotes, but when you drew them on your test, you didn't space them quite right. I actually kind of messed up too. I think these two on the left are a little too close together. See what I mean? I didn't make them equally spaced. So some of you did that on the test too. But I can fix mine by dragging this over. There we go. Except then I move this asymptote. Let's move this over. Ooh, that's cool. Let's move that over. All right. That's goofy. Okay, so pi over 2, negative 3 pi over 2. Make sure your spacing's correct between them. All right. Then we have the 3 branches, the first 3 anyway. We got this one here. It's not a cubic. So this function, is this 1-to-1? Is this thing 1-to-1? No. Bam, bam, bam. 3 contacts already. Not to mention all the other branches, right? Okay, so this is not 1-to-1. Y equals tan x is not 1-to-1. But it isn't hard to make it 1-to-1. What would we need to do? We just restrict our domain. That's what it's called, restrict the domain. Let me erase this red line. We'll restrict the domain, choosing what do you suppose we would choose?
The one that crosses the y-axis, the origin.
Yeah. So most people agree that we would choose just this piece only for a principal graph that we can invert and call a function. So we will go ahead and call this y equals capital tan x, and we'll describe it here. So y equals capital tan x has domain. Careful. Be very careful.
Domain all. No.
Domain. We're restricted by 2 asymptotes.
Negative pi over 2.
Negative pi over 2 and pi over 2. Inclusive or exclusive? Yes, we cannot include the asymptotes. So that red graph lives entirely between negative pi over 2 and pi over 2 exclusive. Okay, range is all real numbers. So you can write negative infinity, infinity if you prefer that. Okay, let's talk about the graph of arctan, or inverse tan. So y equals inverse tan of x, also known as y equals arctan, is going to have the following domain. All real numbers. And for range, negative pi over 2 is less than y is less than pi over 2. Okay? So let's see if we can draw this. I can't draw a green box around the principal tan. Why not? It's infinitely long. I can't draw a green box around it like I did last time, so I won't try to. But we understand the domain of range. That's good enough. So we'll just go ahead and put in pi over 2 and negative pi over 2. These, by the way, are now horizontal asymptotes. Even the asymptotes reflect. Vertical lines become horizontal. We know there are some points on the principal tan wave that are in quadrant 1 and others that are in quadrant 3. But this graph does entirely spends all of its time in these two quadrants, right? So the reflection will still be in these same two quadrants. We said at quadrant 1 point it will reflect over to quadrant 1, quadrant 3 into quadrant 3 still. The origin will just stay right where it's at when it reflects. So we're going to have basically a graph that looks like that. And we've got to watch the curvature on this. This is a little bit easier to do. It has to go like this. If this is going to pass through the origin, right, and yet avoid the asymptotes, and there's an arrowhead in quadrants 1 and 3, we don't have much choice but to draw it like this. Unless we add lots of goofy like bendies and stuff. We don't want that. It's a pretty simple shape. And there's your graph. On this one, at least 3 points, please. Besides the origin. He doesn't count. Or, actually, go ahead and give me 2 more points. I care a little bit less about the points on this one. So give me, like, where you think negative pi over 4 is, and, you know, positive pi over 4.
Piecewise functions.
That's a possibility, but that's not the focus right now. That's a good question. Okay, so your job is to, and don't forget to describe the parity, odd, even, or neither. Okay, so your job tonight is just to make 3 flashcards. That's all you have to do. Make them nice. I've asked you to add to what I've got here, and of course scale it better than I did. I just freehanded everything. So try to get it looking nice. Some of you need to make your first decent flashcards of the year, because I've been getting some real junk. Okay? Make them nice so you can remember these well. These, honestly, after I test you on Chapter 6, you'll put these away for a year. But when we come back to them in calculus, they're very, very important. All of them. And yes, there are 3 more: inverse secant, inverse cosecant, inverse cotan, right? Okay.